If you haven't already done so, please print this handout. We're going to talk about factors that affect solubility and rate of dissolving. So two different ideas here. Solubility, how much of your solute can be dissolved in the solvent, and rate of dissolving, how fast that dissolving happens. So as you know, there are some solutes that will not dissolve in certain solvents. For example, oil and water. And the reasons why a solute may or may not dissolve in a solvent are related to the intermolecular forces between the solute and solvent particles. Remember, intermolecular forces, these are things like ion-dipole attractions, dipole-dipole attractions, hydrogen bonding, things like that. And the general rule is like dissolves like. What I mean by that is when we talk about if a molecule is polar or nonpolar. So if you have a polar substance, it will dissolve in a polar solvent. A nonpolar substance will dissolve in a nonpolar solvent. Like dissolves like. You cannot dissolve a polar substance in a nonpolar solvent, and vice versa. You can't dissolve a nonpolar substance in a polar solvent. If you think about an ionic compound like sodium chloride, salt, you can dissolve that in water, which is a polar solvent. However, you wouldn't be able to dissolve salt in oil, which is a nonpolar solvent. And this has to do with the intermolecular forces that are occurring. And that's what I'm going to spend some time looking at right now. So I want to start by talking about dissolving an ionic compound. So my example is going to be dissolving salt in water. The electrostatic forces holding the ions together must be broken. So remember, in sodium chloride, you have sodium ions and chloride ions that are attracted to each other. This is called an electrostatic attraction or an electrostatic force. It's the attraction between positive and negative charges. When you break that, that's called dissociation. So that force needs to be overcome in order for salt to be able to dissolve in water. Water is a polar molecule. If you'll recall from a few units ago, there's a slightly positive end and a slightly negative end in our water molecule. It's polar. And there's an attraction between the negative side of the water molecule and the positive sodium ion. So this is called an ion dipole attraction. Every water molecule is a dipole. It has a slightly negative pole and a positive pole. For the chloride ion, since it's negatively charged, it's going to be attracted to the slightly negative side of the water molecule. But still, we have an ion dipole attraction. So again, we have sodium ion and a chloride ion, and those ions are attracted to the water molecules, which are dipoles because they're polar molecules. And we would say that these ions are hydrated. Hydrated just means they are surrounded by water molecules. Hydrated ions move through the solution and they conduct electricity. And this is called an electrolyte. So ionic compounds are called electrolytes because when you dissolve them in water, they will conduct electricity. But let's talk about dissolving molecular compounds. Just like when we were dissolving the ionic compound, we had an ion dipole attraction. now we have dipole-dipole attractions. Or remember, there's a special kind of dipole-dipole attraction called hydrogen bonding. So for example, dissolving methanol in water. I'm going to draw it out for you. So here I have a molecule of methanol, and here I've just drawn two molecules of water. But basically with a methanol molecule, you have this OH structure. Well, that's a polar bond right there between oxygen and hydrogen. The oxygen is more electronegative than the hydrogen, so the oxygen is going to be slightly negatively charged. The hydrogen will be slightly positive charged. The same thing happens in the water molecules. So what you see is this negative charge on the oxygen is attracted to the positive charge on the hydrogens in the water molecules. And the oxygen atom in the water molecule is attracted to the slightly positively charged hydrogen on the methanol molecule. So what you have is a dipole attracted to a dipole. This is a dipole-dipole attraction. And if you'll remember from Unit 1, hydrogen bonding is just a special kind of dipole-dipole attraction where you have oxygen bonded or attracted to hydrogen. So I've actually shown a hydrogen bond here. These compounds, so molecular compounds, when you dissolve them in water, they don't conduct electricity. So we call them non-electrolytes. So if you dissolve an ionic compound in water, it's an electrolyte, meaning it conducts electricity. If you dissolve a molecular compound in water, it's a non-electrolyte. It won't conduct electricity. Salt water conducts electricity. Sugar water does not. So intermolecular forces affect solubility. There are some other factors that we'll talk about if you flip over the page. There are three main factors that affect the solubility of a compound other than the intermolecular forces. And these are temperature, particle size, and pressure. So if you increase the temperature, a solid will be more soluble. Liquids doesn't really get affected by temperature a whole lot, but gases, it's the opposite of what it is for solids. And if you remember from the last lesson, I talked about this when I showed you the solubility curve. You can dissolve more solid in water as you increase the temperature of the water. Gases, it's the opposite. Think about that can of pop sitting out. As it gets warmer, less carbon dioxide is dissolved in that pop and it gets flat. Particle size, this is something that you know already based on experience, I'm assuming. If you have a powder versus a big chunk, you're going to be able to dissolve the small particles, the powder, better than the large chunk. Pressure, again, think about a pop can. When it's under pressure, all that gas is dissolved in the water. When you open the tab, now you've decreased the pressure and all that gas bubbles out. It can no longer be dissolved in the water. So the solubility of a gas decreases as you decrease the pressure, and vice versa. The solubility of the gas increases as the pressure increases. When we talk about ionic compounds being dissolved in water, though, there's the ion charge that you have to think about, as well as the size. So a larger charge on an ion will make that ion less soluble. And when an ion is larger, it will be more soluble in water. So I'm just going to show you the reasons why that is. So when we're talking about the charge, as you increase the charge on the ion, That just means there's a stronger force that holds those ions together. Because the force is stronger, it takes more energy to dissociate the ions, meaning it's less soluble. So if we compare a sulfide ion with a chloride ion, well, a 2- charge is a bigger charge than a 1- charge, so that one is more soluble. The next set, we have a 2- charge and a 1- charge. The 1- charge is more soluble. And when we think about ion size, small ions bond more closely together than large ions. So if they're bonded more closely together, the bond between small ions is stronger, which means it takes more energy for small ions to dissociate. More energy to dissociate means less soluble. So the smaller ions are less soluble. The larger ions are more soluble. So if we look over here, let's compare a nitrate ion versus a hydroxide ion. Which one's bigger? Well, you've got 4 atoms in this ion and only 2 atoms in this ion. If we compare sulfate with sulfide, this one's bigger, so the bigger ones are going to be more soluble. Next, I have an example where you're going to apply what you learned about right here. So here I have sodium chloride, sodium fluoride, sodium iodide, and sodium bromide. And you're to list these in order of increasing solubility, so from least soluble to most soluble. Same idea over here and over here. So use the idea of ion charge and ion size to differentiate. Pause the video and try that. I'm going to put my answers up and you can see. For the first set, the charges of the ions are the same. We have 1+, 1-, 1+, 1-. So we have to differentiate based on size. So remember, the larger the size, the more soluble. So the largest ions are the most soluble, the smallest are the least soluble. For the next set, we are differentiating based on charge. The sizes are relatively the same, so we're going to base it on charge. So remember, the larger the charge, the less soluble. And the last one, it's a little bit tricky. It's kind of a combination of both. So yeah, you really got to think about that one. If you have questions, you can email me. But let's move on to the next section. Talking about the rate of dissolving. So this is just how fast or how quickly the solute can dissolve in the solvent. So there's 3 things again: temperature, agitation, and surface area. These are all different things that can speed up or slow down how quickly your solute can dissolve in the solvent. So if you heat up the water, you're going to be able to dissolve the sugar faster, for example. If you mix it or shake it, stir it, the word is agitate, you're going to be able to dissolve the sugar faster. Surface area, if you think about a powdered sugar versus a sugar cube, the powdered sugar is going to dissolve faster because it has a higher surface area. There's more area of the sugar in contact with the water at any given time. So those can be your examples. So there you go. You can move on to the next section of the activity, and if you have questions, please email me.